I changed my title many times during the last 2 days. I wasn't sure what I would talk about. Finally, I decided this is such a serious conference. I would try to amuse you at least a little bit. So, the final title is Categorical Symmetries in Loop Soups. And loop soups are typically this kind of thing. Oh my God, it's really a pointer for smart people. Huh? And they may also involve spaghettis. So loop and spaghetti soups. I'll focus on loops. I have nothing against spaghettis. Just don't mix the two dishes. This is my advice, even if you're eating Scottish food. So this is a very classical problem, and classical in many ways. Classically, loop soups and spaghetti soups are a problem that's really 40 years old and more, and it's a problem that occurs in a variety of physics and mathematics contexts, from the theory of polymers and the work of de Gennes to reformulations of formal quantum field theory a la Fröhlich and Spencer, to probability theory, and that's probably this angle you know most, right? Probability theory. There's been, I've stopped counting, 2, 3, 4 Fields medals in this field of probability theory and random motion and interacting random motion and all that. Of course, it's a very interesting problem. It's also, loop soups also occur in a quantum context, as you also know. There's a way to describe ground states of many systems of interest for topological quantum computation, like Tori code, in terms of loop soups, and there's also been plenty of works in this area, some of which are mentioned here. So this is the general context. I'm not interested in topological quantum computation. I apologize for this. But somehow all my work is related with stuff that people are using in the field. That's part of why I'm here, I guess. In fact, I'm also here because I'm an old friend of the organizers, I suppose. So my goal is not to discuss topological quantum computation, but old-fashioned stuff, mostly the CFT description and the behavior of renormalization group flows in this model. So think of this talk as a kind of illustration of the concepts you are used to dealing with, but in a more traditional setup of physics. So why, anyway, would we be interested in loop soups? Well, the real reason I'm interested in them is that they tend to be described by conformal field theories when you consider them in 2 dimensions. And these conformal field theories are non-unitary, non-rational, and non-quasi-rational. They are very difficult conformal field theories, and they are of interest, of course, for a variety of mathematical reasons. In particular, the CFTs are typically associated with non-semi-simple fusion properties. There are some examples of non-semi-simple quantum field theories, and this is something very interesting. And of course, they're also interesting for physics problems, in particular, all the physics of disordered non-interacting electronic systems in 2+1 dimensions can be formulated in terms of the properties of loop soups. This is globally why we are interested in loop soups. So, like I said, even though the topic is not topological quantum computation, many of the tools and ideas are common with the field of topological quantum computation. And in fact, what I wanted to do today was focus on generalized symmetries. So this concept of generalized symmetry or categorical symmetry, which we are familiar with coming from the study of topological insulators, topological quantum computation, and so on, is also something that has a life of its own in interacting non-topological theories, be it field theories in higher dimensions or conformal field theories in 2 dimensions, and this is mostly what I want to discuss today. So this is based on work with many people, some of whom are here, and others whom I probably forgot to, whose names I probably forgot to write, but I'll mention them when the time comes. And if you wonder where I am, well, right now I am Université Paris-Saclay, the new thing in Paris-Saclay, which nobody really knows what it is, but it is a conglomerate of many, many things built essentially in order to rise through the ranks, and we are associated with the math department in particular. All right, so let's start with some concrete stuff. What is a loop soup? Well, a loop soup in 2 dimensions is a set of self-avoiding, mutually avoiding loops, which define a statistical ensemble, and the statistical ensemble is built typically in such a way that you give a fugacity per loop. That's non-trivial. It's sometimes called D in the field of topological quantum computation. A fugacity per loop, which I'll call N, and then a fugacity per monomer. Okay? So I'll be a little bit more precise a little bit further down the road. But this is an example of a loop soup. And the typical problem you are interested in is calculating correlation functions in this loop soup, various statistical properties. Loop soups can be drawn in the continuum. They can be drawn on a lattice. The hexagonal lattice is honeycomb lattice is particularly nice for this. And here is a bigger photo, a bigger picture of a loop soup, where you see that the loops typically, if the fugacity of the bonds is large enough, if you have many bonds, if you fill up the system, are fractal objects. That's why they're interesting. In fact, generically, a loop soup is a critical object described by conformal field theory, and the type of observables you may consider in a loop soup could involve, in particular, opening the loop to make a spaghetti and create what you would call in another context anions. These loop soups are standard in many problems of statistical physics, and I will talk about the so-called ON model much further in a few slides. The Q-state Potts model, in particular for percolation, hence Fields medals, and disordered free electron models that are mentioned already. And they are, of course, a big thing in probability theory. So the properties of loop soups are difficult, very difficult to understand. The progress in mathematics has been done using SLE, which is mostly solving problems near a boundary, solving an interface problem. Physicists are really interested in the properties of loop soups in the bulk, far from any boundary, and this creates a lot of difficulties. I'll talk about this a little bit later. But of course, in the non-rigorous setup, there's been quite a bit of progress, in particular using methods of Coulomb gas and whatnot, and more recently using a technique called the bootstrap, which I decided not to talk about. It's of course a very powerful technique, and I think by now we almost understand these CFTs completely. And like I said, we know they are non-unitary, essentially because there's some sort of non-locality in the mere definition of the model. They are non-rational, and they are non-quasi-rational, which means typically OPEs give rise to an infinity of primary fields, and moreover, they are non-semi-simple, so it's not fully reducible in the language of algebra. But we are not going to worry about any of this. What I want to worry about mostly is symmetries, and I want to illustrate, like I said, the role of topological symmetries in this context. Are there questions about any of this? Yeah.
Are those pictures meant to represent states in some kind of classical configuration?
So this is a classical. Sorry. This is a classical statistical mechanics description, right? Therefore, this is a configuration. We're going to write the partition function in a minute. Of course, you could do a quantized version of this problem by having a time slice here, and then the configuration will have something to do with temporal-Lib algebra, something we'll discuss in a second. So I will get back to you. In fact, I have a lot of comments about your talk. All right. Other questions? All right. So there are various ways to tackle these problems, and the way these loop soups occurred in physics was via the study of the ON model. So the ON model is an old problem of physics which describes essentially the life and phase transitions of systems where the local order parameter, instead of being a magnetization, which is a scalar in the Ising model, is a vector with n components, and the theory has a symmetry, which is the orthogonal group. Okay? So there are generalizations of the ON model involving the spin S with an arrow instead of plus or minus for the Ising model. And of course, the field theoretic description of this model is a Landau-Ginzburg description, with a order parameter that has ON symmetry. Now, you won't need to understand any of this, just some very general features, like the Ising model, the more general 5⁴ theory with a order parameter having ON symmetry in 2 dimensions has a phase transition if n is smaller than 2. So there's the Mermin-Wagner theorem, which probably you know, that says that in 2 dimensions, classical statistical mechanics, you cannot break spontaneously a continuous symmetry. That's a theorem which is deeply relying on unitarity. So one of the things we will have to do is to extend the definition of the model from n integer, which makes sense for ordinary orthogonal groups, to n not an integer. Okay? So this is something that's familiar in physics. It can be done more or less rigorously in mathematics. I will go back to this issue also a little later. But you see, when you want to, when you want to look at these loops and give each of these loops a fugacity n, a real number, and you want to interpret this as a model with an ON symmetry, you'll be forced to do something about the meaning of ON where n is not an integer. In fact, to a very large extent, the model can be defined with n complex, and I will get back to this a little bit later. So, bearing this difficulty of giving a meaning to n not integer, what is interesting is that if n is not an integer, you escape the Mermin-Wagner theorem because the theory is not unitary. It's not unitary for a variety of reasons, but if you wish, the best way to think of it is it's not unitary because n is not an integer. I can get back to this. And if you escape the Mermin-Wagner theorem, you can have a phase transition. So the phase transition, the critical system that describes the long-distance properties of the soups, can be understood if n is not an integer by thinking of the critical point of a Landau-Ginzburg theory with ON symmetry and n not an integer. Okay, that's a technicality, but it's an important technicality because it suggests that you may want to think of this loop in the language of the orthogonal group and the ON symmetries. Alternatively, there's something to be said about a sigma model, but maybe it's not really appropriate for this audience. But the point is, again, that you would easily see that there is a phase transition. So in these models, there is a phase transition where the model is critical. It is the equivalent of the Ising phase transition. And then there's a low temperature phase where you may expect that the symmetry is spontaneously broken. All right. Now let's go for maybe a slightly more convincing description of the ON symmetries in these models, but it's very simple. If you define a model whose partition function is, so you're going to put a spin S on every vertex of your lattice, Si with an arrow because it's an n-component vector, and imagine you define your partition function as follows. You integrate over all the spin configurations, and then your interaction is simply 1 plus ksi.sj, where the sites I and j are neighbors. So this is not an exponential. It's like truncating the exponential to the first term in the Taylor expansion. If you define your partition function this way, it's a very easy exercise doing standard high temperature expansion to see that the partition function can be rewritten as a generating function of configurations of loops that are self-avoiding and mutually avoiding, with a fugacity k per edge and a fugacity n per loop. N because n components can travel around the loop. Okay? So this is the ON symmetry origin of the loop soup definition of the model. And like I said, this model is critical if the fugacity k takes a special value. It's pretty clear if k is very, 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 very small, you won't have any loop. And then you increase k, at some point the loops start really becoming big and bumping into each other. That's where you're going to be critical, and that's the TFT we're interested in, even though we will also be interested in the phase where k is larger than its critical value, which also turns out to be critical. So once you have done this, you can define easily the analytical continuation of the model if you are given a partition function or a correlation function. What you do is you calculate it in finite size for n integer. You have the value for all n. The analytical properties of the partition function allow you to continue uniquely to n real or complex, and then you take the thermodynamic limit. The order is important, by the way. Okay, so n equals 0 describes self-avoiding walks because you have no loops. What you may have is maybe one line, and that's also, of course, something the SLE community has been very interested in.
I think there's a question.
What do you mean by unitarity of the model?
By unitarity?
Yes.
Okay, so that's, of course, a very good question. So the Boltzmann weights are positive, but even though it's not so obvious, the way we define the model by this generating function is non-local. It's non-local because if you are given two pieces, they may or not belong to the same loop, and this information is a non-local information. So if you have two pieces next to each other, they may be parts of two different loops, or one loop defined by going very, very far around. And to find out whether it's one loop or two loops, you really have to go very far and look around. So that's the first observation, is that it's not really totally local. Now there is a way to make the problem local by twisting a bit the definition of the Boltzmann weights, introducing in fact complex Boltzmann weights that immediately would break unitarity. That's one way to see it. Another way to see it is simply to say that if you go to a quantum field theoretic description, you will have in the OPEs and so on residues which will typically involve Casimirs and higher Casimirs of ON. And if n is not an integer, it's easy to prove that for any n not an integer, some of these Casimirs will become negative. So you lose positivity in the OPEs. That's another way to say something. Going to the Hamiltonian description, to the 1+1 quantum field theoretic description, it means exactly that. The Hamiltonian is not Hermitian. So in terms of a quantum mechanical description, the probabilities are not all positive. They're all real, however, but they can be positive or negative. So, but as a stat-mech model, it makes perfect sense. So it's interesting to wonder how the quantum field theoretic description can be used even in this context. And of course, if you want non-semi-simplicity of the quantum field theory, you need to break unitarity. With unitarity, you will always have semi-simplicity. So that's the long answer to the question. Other questions? All right. So a point that will look like a mere technicality but will be very important for me is the issue of crossings. So these loops I defined as self-avoiding and mutually avoiding, but I could have been much more general. It's a general result that if you take a Brownian motion or a Brownian loop soup, so imagine I defined the so-called conformal loop soup, but I could also have defined a Brownian loop soup. A Brownian loop soup would have consisted in taking the same object, but now the loops would be Brownian loops. Okay? So the loops, each loop could intersect itself many times, go over the same edge many times, and then loops could overlap. Okay? This Brownian loop soup is another system, also described by conformal field theory. Not very interesting. It's very easily solvable. But the point is, if you take a Brownian loop soup and if you introduce any kind of short distance repulsion, for instance, you add a little cost for a loop to go twice over the same edge, immediately what happens is that the long distance properties are described by fully self-avoiding loop soup. So there is a flow in the sense of the renormalization group between the Brownian situation and the self-avoiding situation. That's why it's nice to start with the self-avoiding situation. So when I say self-avoiding, I mean self-avoidance on the edges and on the vertices. And now there are various interesting questions that one may ask, and one of them is related with crossings. So the model I took is a model that's very simple because I defined it on the honeycomb lattice where not even crossings are allowed. I could also, if I decided, add crossings and define instead the model on the square lattice. Okay? The claim is that the long distance properties would be exactly the same for this model and for that model. And that's a very important point that I will interpret algebraically very soon. So the two critical points are the same, and they are called, by the way, the dilute critical points. Once again, you start with k very small, and you increase k until you reach a critical point. The fact that these crossings don't matter in the physics language means that the four-leg operator, the operator associated with those crossings, is irrelevant at the fixed point. And it's called a dilute fixed point because you could decide to go further. You could decide to increase k beyond that critical value. So you're jamming in loops, but these loops, all of them want to exist. They want to grow arms and legs and whatnot, and they are bumping against each other. And it so happens that this phase is also critical. It's also critical. It's also described by conformal theory. That's called sometimes the dense phase. And that, now, the same question we asked about crossings could also be asked in the dense phase. And it so turns out that even though at the dilute fixed point the crossings are not important, in the dense phase the crossings are very important. So there is, to summarize in this model, three interesting conformal field theories. There is the dilute critical point, there is the dense critical point where you increase k beyond kc, and there is yet another critical point we discovered with Jacobsen and Nick Reed many years ago, which is reached if you add a tiny bit of the four-leg operator. So although I said that at the dilute fixed point crossings don't matter, the instant you allow k greater than kc, the RG flow doesn't go to this dense fixed point anymore, but it kind of turns around and goes to yet another fixed point, which is really the fixed point of the spontaneously broken ON symmetry. It's really the ON over ON minus 1 sigma model. Okay, so this is a fact, and in fact the essence of this talk is to understand this fact, understand essentially what is preserving the flow from the dilute to the dense model when we don't allow crossings, and what happens when we allow crossings. Because you see, crossings are not very different from that's a joke. A crossing is really not very different from this. So when you look at a system at large distance, you may wonder how come crossings play such a role and configurations like these don't play the same role as crossing. This is a bizarre property that I will make much more formal soon, and that's what has to do with topological symmetry and non-invertible symmetries. Okay? So that's the general context. My goal is a physicist's goal, but don't worry, we're going to do algebra very soon, and the physicist's goal is to understand the nature of these phase diagrams and what crossings mean in terms of symmetries. What does it mean to allow crossings or not allow crossings? Questions?
Sorry, can I ask? So when you say crossings here, you mean meeting at corners on the square lattice?
Yes, for instance.
And with the honeycomb lattice, what does it mean? Or we don't have anything
They are not
at
there.
this stage?
They're really prevented, but you could have, they're really prevented by the topology of the lattice. So this is a case where somehow you can never have crossings. Yes, that's all I can say. Yeah, it's not a nice lattice. I mean, it's nice, but anyway, for this discussion, it's really a little bit marginal. Other questions?
Is there some nearby phenomenology you could mention? So whenever there's a renormalization group flow, and it depends heavily on what things you allow to turn on.
Yes,
then
absolutely.
you're thinking about phenomenology. So
This
why would that thing not?
This is going to be the point. What prevents me from? What is it exactly that's making the difference between these two things? And how can I make sure that these don't look like crossings at large? This, in a slightly more RG language, what is it that prevents the generation of crossings under the RG flow? And we will see that it is non-trivial. But thank you for your question, because another immediate point is, you see, when you look at a loop soup in 2 dimensions, it's a loop soup on the surface of a sample. It's really 2-dimensional. But imagine looking at 2 planes both containing a loop soup. If you look at this plane from above, then you will see that you have, in fact, crossings. So hidden behind this is the result that the universality class is really only stable exactly in 2 dimensions. And if you went to 2 plus epsilon, immediately you would be reaching that other fixed point. which is again something I will interpret in terms of symmetries. All right, so now let's.
Can I just ask a quick
Sure.
question?
Back to
You
physics.
wrote the dense phase is not the generic low T phase for this ON model. So
Yes. So
are you saying it doesn't appear in the ON
if you had a generic, so this is going to be the essence of the talk. The essence of the talk will be that the model with no crossings is not ON generic in a sense that I will make precise. If you had a generic system like the Landau-Ginzburg or the sigma model, and you looked at the low temperature phase, it would be the sigma model, or it would be the spontaneously broken ordinary Goldstone mode theory, ON over ON minus 1. So the point is, the dense phase where you don't allow crossings is not this model. That's what I mean.
So is there like some non-generic ON model that you can write down?
I will explain this. Very good question. I explain this right now. All right. And so what is non-generic about the model without crossings? Well, all this business about loops, high temperature expansion and so on, of course, has a formal analog, which probably you will feel a little bit more comfortable with. It is Chauvel duality and the Bauer algebra. So if we now go from the 2D statistical mechanics description to the 1D quantum description, we're going to have a Hamiltonian acting on a certain Hilbert space, which typically we will, so there will be a little subtlety here, but let's start with the simplest case where we have packed the loops as much as possible so that every edge is occupied. In that case, the Hilbert space is simply the tensor product of the fundamental representation of ON and a generic Hamiltonian with ON symmetry will be an element of the Bauer algebra. In fact, the set of operators that commutes with ON on this Hilbert space is the Bauer algebra. That's the Chauvel duality in that case. Okay. So if you think of the Bauer algebra, I'm sure all of you know this, but just to make sure, remember that in ON, when you do the tensor product of two fundamental representations, you get three possible fusion channels: the identity, the fundamental, and the symmetric representation. Three channels means, if you want to represent this in terms of diagram, that there are essentially three diagrams naturally associated with interactions preserving this symmetry, and there are the identity, the construction, a temporally element, and then the exchange of the two representations. Now, as you know, the Bauer algebra is generated by these three objects. Okay, so the theorem is that there's a Chauvel duality between the Bauer algebra and the action of ON on this Hilbert space. Now, a technical remark, I keep playing with the dense model where the loops are fully packed, and the dilute model where some edges are occupied, some edges are not occupied. Algebraically, this corresponds to dealing respectively with what's called the Bauer algebra and what I will call the dilute Bauer algebra. I'm sure there's a fancy name for it, but maybe not. In fact, there's dilute temporally, there's dilute Bauer, there's dilute everything. And what this means is that we're looking at the Chauvel duality, not on the tensor product of fundamental to the L, but on the tensor product of the sum of the trivial representation and the fundamental representation to the L. Okay, and I think that's probably a paper by Georgia Bankart discussing the Chauvel duality in this case. So there is a version of the algebra which is dilute. Dilute means you still have lines, you still allow only these interactions, but some edges may be occupied, some not, or in the quantum version, some points in the Hilbert space may be carrying a line and some of us may not. Okay? So this is the general setup, meaning a general system with ON symmetry is related with the Bauer algebra, and the Hamiltonian is an element of the Bauer algebra. Now, first question is, if we want to forbid crossings, what happens to the Chauvel duality? This is where the problem started. So we have duality between Bauer and ON. You take Bauer and you say, oh, I don't want crossings anymore. I only want the temporally elements. What happens to the Chauvel duality? Well, it may look like it's simple, but it's not. It's not, and this is a crucial remark I want to make. In general, when we are interested in studying bulk properties of conformal field theories, we want to put our lattice systems on a ring. Now, typically in your talk, you were considering domains that were open, and this was allowing you very nicely to embed f into f prime and so on and so forth, right? When you want to close the system and look at periodic boundary conditions in a physicist language, annular algebras in a mathematics language, you are encountering difficulties because you cannot immediately embed one algebra into the other, right? But nonetheless, this is what we want to do in this problem. We don't want really to reduce Bauer to Temple-Elib. We want to reduce Bauer to a version of Temple-Elib defined on a ring, the annular version of Temple-Elib. Okay, so there are various ways to think about it and talk about it. I think probably the paper with the algebra I'm interested in was first defined was the Von Jones paper about the quotient of the Hecke algebra. It is also a quotient of the more general algebra called the affine Temple-Elib algebra. And in fact, in the physics literature, it has tended to be called the Jones Temple-Elib algebra. Okay, it's the Temple-Elib algebra with two more generators, in fact. So Temple-Elib, of course, just you all know what Temple-Elib is. Jones Temple-Elib algebra is a quotient where, well, first of all, you need to add elements. So now we are having our words defined on a ring, so we can close the ring by going around the system, right? We are having a bunch of lines, and then we have generators like this, but we're also having generator like this, the periodic generator, so to speak, and there are relations associated with this that I won't write down. And then there's also the translation operator, because when you are on a ring, you have naturally translation symmetry, right?
Do you assume a full,
So-
by rotation the identity?
So there are various quotients. The relevant quotient for this physical system is that we want everybody to have just the weight n. So loops wrapping around the system still have the weight n. I could modify it, I'm not going to. And then when we have through lines wrapping around, they also don't get some extra weight. So this is precisely what we call the Jones Temple-Elib algebra, and this is exactly the quotient that Vaughan was considering in his paper. All right, so I guess, I don't know, maybe 2 minutes just to define the modules very briefly, to fix notations. So the modules of this algebra are defined by two quantum numbers. One is the number of through lines. I use this weird parameter r, so that 2r is the number of through lines. And then when we're having a given number of through lines, even though when we all wrap them around the system, we don't get a phase, if we only wrap one of them around the system, we may get a phase. And that phase is parameterized by e to the I pi s. And the constraint that when you wrap all the loops, all the lines around the system, you don't get a phase, is the constraint that t to the 2r is equal to 1 in this quotient. And I couldn't resist citing our old paper with Paul. I won't tell anecdotes about our first works together, though maybe tonight. Oh no, the banquet is tomorrow. Okay. So anyway, these are the modules. Okay, so what is non-generic in the model is that I don't want to allow crossings. So from the point of view of symmetry, yeah, I'm just checking the time because this is not on time, and I'm okay. I think I've talked for a half hour so far, right? Okay. So for a model with generic ON symmetry, the Chauvel duality would tell us that the Hilbert space, I will not make the distinction between dilute and dense from now on. I'm only going to talk about dense, I think. The Chauvel duality would tell me that I can write the Hilbert space as a bimodule, which is a sum over modules of the Bauer algebra and modules of ON. So these are, the lambdas are representations of ON, and the BL lambdas are Bauer modules. The Bauer modules are indexed by partitions, and they are typically determined, Bauer modules, by giving some information about which point is connected to what point. This one is connected to that one, this one is connected to that one. And as far as the through lines are concerned, well, the through lines can cross each other any way they want, so of course you can parameterize the representation by a representation of the symmetric group on a number of through lines, and that's how you get these modules. Okay, so from a mathematical point of view, forbidding crossings amounts to restricting the Bauer algebra to a sub-algebra, which is the Jones-Temple-Ellipse algebra. So the problem, if we wanted to understand better the nature of the Hilbert space, is to find the branching rules from the Bauer algebra to the Jones-Temple-Ellipse algebra. Surprisingly, the problem doesn't seem to have been studied by mathematicians. We asked around for help and didn't get any. So we did find a combinatorial formula for this. It's complicated. I am not going to show it. I show a slightly different formula later on. But the essence of it is, of course, that this is not an easy problem. In particular, if the number of through lines is equal to the number of sites, then the representation of Bauer is the same as the representation of the symmetric group on L objects. And what you want to do in that case, since in Jones-Temple-Ellipse you're not allowing crossings, all you're allowing is going around the system, what you want to do is find a decomposition of the modules, the special modules of the permutation group into representation of the cyclic group, right? Already not a totally trivial problem, though it's been solved 20 years ago. And our problem is, if you wish, a generalization of this problem. So there is a formula for this. It's not particularly illuminating, but I'll comment it later. The point I want to make at this stage is that the coefficients don't depend on n or don't depend on L either. So when I was saying, oh, I'm worried that n is not an integer in my definitions of the model, at this stage, notice that I don't give a damn. N could belong to C. The Bauer algebra is defined for any n. And in fact, one of the ways to define these models for n arbitrary is to go from the concept of ON symmetry to the concept of Bauer category, in fact. I'll say a little bit more about this. Yeah.
The lambda could be arbitrary. Is there going to be some restriction on lambda?
Sorry?
So when n is not an integer, the lambda will be modules over blah.
What about the lambda?
Is there any restriction on lambda?
R goes, so R is the number of through lines.
Yeah.
It goes, no, 2R is the number of through lines. So it goes, so like I said, the representations are indexed by the representation of the symmetric group on the through lines. So that's why the length of the partition has to be at least the number of through lines. It has to be equal to the length of the partition. Or it can be larger. Because when we reduce Bauer to Temple-Ellipse, things that looked like non-through lines become through lines because we are not allowing crossings anymore, so we have to keep properties.
Well, when n is integer, I guess you only want to look at lambda with at least n folds for n. So you have these square brackets for lambda, right?
Yeah, man?
Well,
They're related to L, not N.
Yeah, the only dependency upon L is here and up there because you can have a maximum of L through lines.
yeah, maybe a bit better talk after it.
Okay.
Sorry.
So I don't understand how this Jones-Temple-Ellipse algebra is a sub-algebra of the Bauer algebra because it has the rotation, which I mean the Bauer algebra is just on a string, whereas the Jones-Temple-Ellipse algebra is on a ring, right? So it works on a cylinder. So it's somehow affinized or whatever.
Well, you can represent U with crossings in Bauer. And you can represent the closing word, the E, this one can be represented in Bauer if you allow crossings. So you take Bauer and then you forbid crossing, except for two elements that will involve crossing, and then I will represent them in this.
Okay, so you kind of project your
All right, right. So let's cut to the chase. Yeah. Since Bauer representations get split, ON representations get glued, right? So we had initially this representation of the Hilbert space, and now, sorry, I lost track. Okay, so now these decompose as a sum of representations of the Temple-Lib, which means now that the equivalent Chauvel duality involves now the modules of Jones Temple-Lib, and then things that are bigger than modules of ON. There's necessarily a gluing of modules of ON, and they give rise to gluings of modules that we call lambda big RS, and they are given according to the decomposition here. They're obviously given by these sums here. So in a very naive language, the symmetry is extended. The multiplicities of the fields was ON, given by irreducibles of ON, and now the multiplicities become larger. They become, in fact, these crazy sums here. And now, although as long as I deal with Bauer, I don't have to worry about the meaning of this equality here. If I want to give a meaning to this equality for n non-integer, now I would have to be a little bit careful, right? Because these representations, lambda, like some of his examples here, make sense only for n integer. So I can do various things. I can, first of all, do this kind of decomposition for any n integer. I'm not relying on conformal field theory yet. Or I could, like I said, give a categorical meaning to this thing in terms of traces of projectors in essentially the Bauer category, or a portion thereof, but some bells and whistles have to be added. And in fact, there's a paper by Binder and Rishkov that's handling this difficulty and using what's called the linear category, which maybe is not worth discussing very much. So, but anyway, this can be made rather rigorous. But keep an integer if you want. So here are the mixtures. Now, for a physicist, this is fascinating, because this means there is an extended symmetry. You thought you had ON symmetry, and then you had more, because the multiplicities are more than ON. Here you find the vector representation, fundamental, so that would be the order parameter. Here you find the adjoint, these are the currents, but then you have these complicated structures occurring, and one of the questions we've been struggling with is, what is the extra symmetry? So to summarize the problem, when we have just ON symmetry, we have a Chauvel duality between Bauer and ON. We forbid crossings in Bauer, we get more than ON. What do we get? What do we get that's more than ON? Okay. Couple of remarks I wanted to make. So in the Corey's talk yesterday, I think my interpretation would be that essentially you would forget completely about the multiplicities and you would worry only about the operators. A very reasonable thing to do in some context, but you are essentially losing trace of the symmetry because you are factoring out the symmetry. So what you are losing, what you are gaining is something that I think is an interesting question. But maybe I won't comment anymore here. All right, so the formula, well, I just wanted to say that we know also a formula for these lambdas. It is a little bit gory. Yeah, maybe I won't bother. Okay. So, sorry. Now I lost track. Let's see what was there. Yes. So the fact that the representations get glued into representation of some higher symmetry in a certain way is obvious. It simply means that strictly in 2 dimensions, not all the invariant tensors of ON can be represented without crossing. For instance, if you want to build a field whose symmetry is the fully antisymmetric representation on 3 boxes, well, you need 3 lines, and then you need to sum over all the crossings with all the permutations with the appropriate signs. But it's pretty clear that in 2D, if you don't want crossing, you're not going to be able to do this. So in fact, the field associated with the fully antisymmetric representation cannot be anything else but the same as the field associated with the fully symmetric representation. That's why these two are mixed. With two legs, it doesn't work, because with two legs, instead of a crossing, you can go around. So you can still implement the symmetric and anti-symmetric combination. This is the intuitive idea. Okay, I see people frowning. Okay, you're the most frowning.
I'm wondering about fusion rules.
About?
Like if you can take tensor products of these.
Yes, very good question. Okay, so I'll get back to this. I'll get to this. Okay, so yeah, okay, so maybe just a quick look at the formula. So there's a formula for these big lambdas, and it involves a set of fundamental combinations of ON representations, some of which are written here, which are alternating sum. It doesn't mean much, it's purely formal, and we have the property that their dimension is the same as the dimension of the fundamental representation. So we introduce these specific special representations, and then we define Chebyshev polynomials of these representations. A polynomial is interpreted, so a Chebyshev polynomial will be 2z, and then they are obtained by this recursion relation, so with z squared minus 1 and so on and so forth. And what we mean by a polynomial of this representation is we calculate the tensor product in ON. So for instance, z squared minus 1 means you take one of these lambdas, you square it in ON, and then you look at the result, and if you have a representation that comes with a bunch of coefficients, sometimes plus, sometimes minus, you add them up, and the result is that in the end you only get pluses. So you calculate these polynomials, and then you calculate this crazy sum involving some arithmetics, and the claim is you get this. Okay. So that the proof is actually not that hard, but I won't give it. Okay. All right. So there we go. Okay. So important point: the decomposition whole in finite size is independent of criticality. It's true for large K, for small K. It's true at the dilute fixed point. It's true in the dense phase. It's completely general. All right, so now at this point I would like to go to the CFT, maybe just a tiny bit, since after all you are interested in CFTs also. So what we do is we do this horrible thing that is not rigorous, is to extrapolate from the results we have in finite size to results in a Hilbert space of a conformal field theory. I'm not even sure I should call it Hilbert, because we don't really know what its properties are in the non-unitary case, but there is a procedure to do this, and the procedure tells us that with the decomposition of the space of the CFT, so the continuum limit of this, if you wish, maybe I'll say a bit more about how it's defined later on, and then what happens is that the multiplicities, well, they remain multiplicities. If a field occurs n times in a Hilbert space, it means it's associated with some degeneracy. It still comes n times in a continuum limit. But the other part, the interesting part, is what is the continuum limit of the modules of the Jones-Temple-Ellipse algebra. And the claim is there are modules over the conformal algebra, that is Virasoroth and Virasoroth. How to go from the Jones-Temple-Ellipse algebra to Virasoroth and Virasoroth, well, I've worked a lot on this. I'll have something to say. It's obviously not easy, and it's far from rigorous yet, but there is some sort of procedure. So the continuum limit has this structure of a bimodule just as well, and we know a lot about it. We know in particular that the Virasoroth modules are not fully reducible. So that's a logarithmic conformal field theory. And we know the conformal weights, we know the central charges, and so on and so forth. But it's not really relevant here. Okay, so now I want to go back to the main question of the talk. What is the symmetry? What is the exact extended symmetry that would explain the gluing? And now we've worked a lot about this, and here are some comments. So first of all, maybe to go back a little bit, for those of you who know a bit more physics, it is customary in the unitary case that a theory with some continuous group symmetry at the conformal point would be described by a theory, by a Vesumino theory. That's not true if unitarity is lost, and in fact, the study of the multiplicities shows that the ON symmetry remains global. It's not factorized in left and right symmetry. There are currents conserved currents, Noether's theorem still holds, but there are no independent left and right currents. So instead of having d bar j equals dj bar equals 0, in an ordinary Weser-Minot theory, we would have something like this. Now this is not true. What happened is that d bar j equals dj bar and is a state of 0 norm square. So this is, to answer Arthur's original question, maybe the simplest manifestation of non-unitarity. All the physics is in the ghost sector, or the ghost sector of negative norm square states. That's just the way it is. All right, so question, what is gluing the representations? Is it a symmetry? Well, now Eric's question, no. The lambda s are not stable under ON tensor product. You see it, right? Associated with the question of the tensor product of the lambda s is the question of the tensor product of modules of Jones-Temple-Ellipse, and that's a question we have struggled with for quite some time without much success. It's all good and well and good to define an algebra on an annulus. How do you glue two annuli? And there are proposals for this. We don't really know how to do this. So we don't know how to do the fusion of modules of Jones-Temple-Ellipse, and we don't know. There's no meaning, ON meaning of the fusion of the lambda s. So what is this symmetry has remained for quite some time an open question, and my claim will be that it has something to do with a topological symmetry, though I'm not sure I can fully nail everything with this claim, but at least I can claim some of it. So, should we worry anyway? By the way, the symmetry is not a Yangian, it's, I just don't know what it is. Should we worry anyway? Yes, we should. And that's, in fact, the one of the reasons why the problem is interesting. Is its technical reason, and maybe you will not really fully appreciate it, but remember the renormalization group flow we had. I said that if I don't allow crossings, I'm having a flow from dilute to dense. If I allow a tiny bit of crossings, I'm having a flow to the sigma model. Okay. So when you start with a lattice model, it's possible to not allow crossings, but if you think of it in the renormalization group sense, the question immediately arises, could it be that the crossings are generated under renormalization? For instance, I have this drawing here. Surely if I look at this at far enough a distance, this looks a lot like crossing. What is it that prevents crossings from being generated so that this flow can be observed? And by the way, it indeed can be observed. The dense phase is a very well defined, very well observed phase of the system. Now, usually you would say, well, what prevents the appearance of the four-leg operator is symmetry. For instance, in the Ising model, you know that if you break the Z2 symmetry with an explicit magnetic field, you don't reach the critical theory. But you can argue, yes, but you have broken the Z2 symmetry. If you don't break the Z2 symmetry and you lower the temperature, you will reach the critical. So in general, we like to think that symmetry prevents the appearance of operators. But it would be tempting, therefore, to interpret the absence of the four-leg operator as arising from symmetry. Now, what are the symmetries available? So far as the ON symmetry. And now the problem of all this story is that the four-leg, so in general I had these lambdas RS, which were giving me the multiplicities of primary fields in the CFT. And remember, 2R is the number of legs. So R equals 2 is the four-leg operator. And now it so happens that the four-leg operator comes with a multiplicity that has many representations. So one of them is the symmetric representation on four boxes, okay? So a field belonging to this representation, if I have a Hamilton, that as invariant under ON rotations, this field is prevented from appearing because it transforms non-trivially under ON. But the problem of the multiplicity is that there is a copy of the four-leg operator that comes with the identity representation of ON. Therefore, there is a copy of the four-leg operator that is not prevented from appearing in the RG, not prevented from appearing by the ON symmetry, right? And it's, if you wish, like a magnetic field which would conserve the Z2 symmetry. How would you prevent it from appearing in the RG, right? How would you know it's not there in a system? And that's the puzzle. So the puzzle that forces us to understand better the nature of the symmetry is the fact that a four-leg operator comes with the trivial representation of ON and therefore is not prevented from appearing in the RG if you appeal to the ON symmetry. You have to appeal to the bigger symmetry that glues together the modules of ON. But the question is, what is this symmetry? Is it clear? Yeah, sure? All right, questions?
When you're talking about modules for this affine temporally, are you fixing the number of boundary points, or are you allowing like all different boundary points?
Boundary, you mean through lines, or you mean?
Like literally the number of points on the boundary of
No.
your ring.
So what? Sorry. So with yes, of course, you're. I think the question is that for every size L there is a module, and because it's annulus, we don't know how to embed WL into WL plus 1.
So you don't consider annular diagrams with different numbers of boundary points on the inside?
Yes. I have to think that it's possible without an inclusion. I have to think it's possible to take the limit L goes to infinity and not worry about changes in the structure of the algebra. Now, I would have more to say about this, but of course I'm uncomfortable, but I don't know what it's to do. In sheer algebraic terms, it is very difficult to take the limit L goes to infinity of these guys and get VR0 and VR0 bar. But it's not that it's hopeless. We can do it in some cases. But all right. So
if I've understood correctly, you're hanging the key point on your periodic boundary conditions.
Repeat that. Sorry.
The key point of the difference between just ON and something more is to do with the periodic boundary condition.
I'll comment about this. If we were with open boundary conditions, there would be no problem. Going from Brouwer to Temple-Lib would be essentially going to SU to Q, and that would be the end of the story. But in the periodic case, we don't know.
So what's the phenomenological setting in which boundary conditions are controlled at this level?
So boundaries, remember what I really want to understand is this CFT or the local properties of the bulk theory. So a system with boundaries maps to a field theory near the boundary. So this would be the study of the model near a boundary. And we want the system in the bulk. I mean, that's been from the beginning. It's been the difficulty. All the SLE formalism similarly is able to tell you what happens to a path starting from the boundary. But if you're in the bulk, it's another question. Okay, so a guy like this four-leg operator, by the way, is called dangerously irrelevant in the RG language. And that means it is irrelevant at this fixed point, but it becomes relevant when you approach the other fixed point, and you have to be very careful to make sure it's not there. All right, so in a nutshell, in the last few minutes, I'll try to explain quickly that the symmetry preventing the four-leg operator from appearing is categorical, and it's generated by a non-invertible topological defect line operators. All right, so in fact, it's trivially simple. Let's introduce a topological defect in our loop model as follows. So we're having these configurations of loops, and then I'm going to start by drawing an extra loop or line, and I'm going to represent it as going over everybody else, right? Just something I can draw, and what I mean by this drawing, and I will work in the continuum, it's much easier, although it can be done on the lattice as well, is that I have these crossings, so I'm having my loop model. Here are my loops. Then I say, okay, let me add a topological line by drawing, first of all, an object that goes above everybody else. Okay? Of course, what do I mean by going above everybody else? Well, what I mean is that I have crossings, and I'm going to decompose the crossings in a very specific way with these coefficients, and n is parametric. Q is related with n by n equals q plus q inverse. And then once I have decomposed each of the crossings, I'm going to evaluate the diagrams as before. Each loop is going to have a factor n. Each monomer that was there before will still have a factor k, and then the monomers associated with the extra topological line, I'm not going to give them any fugacity, and they're going to have fugacity 1. It's not crucial, it makes things nicer. So the weights, of course, are not trivial. They are chosen in such a way that the Yang-Baxter equation, the old Yang-Baxter equation, is satisfied with an infinite value of the spectral parameter. What it means is that the weights are chosen in such a way that you can just implement the Reidemeister moves implied by the graphical description. So here's an example. The blue loop is one of the loops I had before. A red loop is the equivalent of my topological line, but now I'm closing it. And then, of course, if you think you can do a Reidemeister move, you're just going to pull these two to give you this diagram. But in fact, the claim is that the weights are chosen in such a way that, in fact, it is exactly what's happening. So you can decompose each of the two crossings. This gives you 4 configurations. And then you observe that since the extra loops have a factor n, topological loops, there is no fugacity associated per monomer, so you don't worry about its length. So the weight of this diagram is indeed n times the weight of the diagram without the loop. This is the topological object. Okay, so that's a cartoon that we can make much more precise, of course, and there are various ways to make this precise. A good way to make this precise is to think about the centralizer, or you shouldn't call it the centralizer, to think of objects, let's think of objects that commute with the Jones-Temple-Ellipse algebra. Okay. So, this cartoon should have been there on the previous slide, sorry. So remember, we're looking on an annulus, and we're having our Temple-Ellipse diagrams. What kind of topological object can I introduce in this setup? Well, I can introduce a loop that goes around the whole system. Okay, this loop, again, I define precisely what it means at the crossings in terms of the decomposition I had on the previous blackboard. And then this loop, of course, commutes with the action of Temple-Ellipse. It commutes with the action of my Hamiltonian. And this loop has a perfectly well-defined expression, by the way. It can be written as a expression of this term type in terms of u, the translation operator, and then the Temple element. So there is the topological invariance, the fact that I can move this loop around, translates algebraically in the Hamiltonian framework into the result that the Jones-Temple-Ellipse algebra commutes with D and D bar. In fact, there's a theorem, okay, maybe I'll write it, it's on the next slide, I guess. Oh, did I miss something? Where's my theorem? Ah, there we go. The theorem is that the center of the affine Temple-Ellipse algebra, so not the Jones, the affine Temple-Ellipse algebra, which is still a bigger algebra where loops going around the system could have a weight different from n, is generated by the operators D and D bar. Put otherwise, all the Juicy Murphy elements can be written as polynomials in D and D bar. So, okay, so these things, D and D bar, commute with the Hamiltonian, and commute with all the elements of the algebra. Now, when I look at the limit of the whole Jones-Temple-Ellipse algebra, it contains, in particular, the conformal algebra, Vira-0 and Vira-0 bar, so I can certainly infer, at least non-rigorously, from the fact that D commutes with the lattice algebra, that it should commute also in the continuum limit with Vira-0 and Vira-0 bar, which is exactly the kind of condition we want to have a topological defect. But of course, the fact that it's topological is obvious. I can move the line and the loops anywhere around. So I have this extra symmetry in the problem that I hadn't thought of before, which I will call a topological symmetry or a categorical symmetry. I have this object D with commutes with my Hamiltonian.
What do you mean by continuum limit of this?
Did somebody else?
Yeah, what do you mean by continuum limit of this Jones
I
temporal
have
Lie algebra?
difficulty hearing you with the mask, sorry.
What do you mean by continuum limit of the Jones temporal Lie
Continuum
algebra?
limit.
You don't mean like you don't mean just taking like a, because you're saying Virasoro's in there, so it's like some.
Okay, so that's really an aside. But the way we're thinking of this is each local interaction term on the lattice belongs to the algebra. And what we think is that, so we have a large Hilbert space. We think that when L goes to infinity, the Hilbert space splits into what we call low energy states, or the scaling limit of the theory, and then the rest. And that low energy space is the Hilbert space of the conformal field theory. Okay. And then the local energy densities, the temporal-Lieb elements, restricted to the action of this space of low energy excitations, coincide essentially with the stress energy tensor of the CFT. So that's in words. Now, there is a procedure to do this. You need to diagonalize the Hamiltonian, and you need a two-limit process. You need first to fix a certain number of states, excited states over the ground state, and you need to define the action of the temporal-Lieb element on this subspace. Then you need to take the limit L goes to infinity, and then you need to take the limit of the low energy space to infinity also. So there are two limits, and in that limit, we think we get the Virasoro algebra as the limit of the action of some combination of the temporal-Lieb generators. So I mean, it's a long story. So there's been quite a few papers on this. There's been papers on the physics side. That's what's been called the Hubert Saleur generators now. And then there's Zheng Han had written, Hubert Zheng Han wrote some papers about this in the case of the Ising model, essentially, which is a free fermion theory. It's a little bit trivial. But there is some sort of non-rigorous procedure that gives us the Virasoro algebra as a limit of the temporal-Lieb algebra once you restrict what we call scaling states. And that's a big problem, of course. And that one more remark about your talk. When you're looking at huge algebra of operators, but of course in the CFT limit there's a sub-algebra, which is the algebra generated by Virasoro bar, and the primary field, and how to extract it is a very difficult question. Anyway, that's what I mean. All right, so just a quick reminder, of course, we know in general that if a theory has a symmetry with some group G, there exists topological defects associated with the elements of the group, which are very simple. What you do is, whenever you cross the topological defect, if you have a microscopic degree of freedom, you rotate the degree of freedom by an element of the group G. If you want to think in terms of states of the Hilbert space, you rotate the state by action of G, and these defects are invertible in the sense that you can build defects associated with G inverse, and the product dG and dG inverse is the identity. Simple example. Model that's flipping the spins. Okay. In contrast, the type of defect we're having here is not invertible, so there is a world that you know as well as me, or better, of wondering about the properties of these defects, and of course, these defects are not invertible, and they satisfy some sort of fusion relations, and that was what's been called categorical symmetry, also outside the context of topological quantum computation. In an ordinary quantum field theory, you can have a topological symmetry or a categorical symmetry. That's a symmetry generated by topological defect lines, and they obey some sort of fusion relation, and here the fusion is obvious. You can define, instead of one defect line, you can have several defect lines going through, and then project them using a Jones-Van Zyl projector, this gives you a family of topological defects. All right, so now blah, 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 blah. Let's go back to the end, the crux of the matter. The crux of the matter is that although the four-leg operator and the four-leg operator comes with the identity representation of an ON and is not prevented from appearing in the RG flow by the ON symmetry, the four-leg operator belongs to a different topological sector than the energy operator coupled with increasing K from the Kc critical value to a value larger than Kc. So the energy operator belongs to this topological sector, and the four-leg operator belongs to the sector with R equal 2, S equal 0, and the eigenvalue of the topological defect operator acting on a four-leg operator is like Q squared plus Q to the minus square. So, because of this, four-leg operator and energy operator belong to the same representation of ON, but belong to different representation of the topological symmetry. Moreover, it's a subtle point but very crucial, the energy operator belongs to the sector of topological symmetry called D11, is the sector of the identity, and moreover, all the OPEs of the energy operator with itself, we can prove, also belong to this sector. So in the RG, you're never going to generate operators outside of this sector. So the two-leg operator, the four-leg operator, and the energy operator belong to different topological sectors, and you can do any renormalization you wish. This is not going to change, which, by the way, is an interesting question in general. When you have a topological symmetry, how is it preserved under RG? It's really a question that you have to be careful with. But in that case, it is obvious that it is definitely protected. So the point, to answer the question I had asked myself, how do we preserve the symmetry from dilute to dense? How do we preserve the flow from dilute to dense? We preserve it because there's a topological symmetry. So the deep origin of the lambda RS, of the gluing of the ON representation, does not seem to be an ordinary algebra, like a Hopf algebra or something. It seems to have to do with topological symmetry. And I don't know how to define tensor product of topological defect lines, right? So this is the same question. We're going in circles, but at least it's explaining the paradox we were having. Okay, 2 minutes and I'll be done. Okay, none of this is interesting. Okay, further notes and a quick conclusion. Well, first of all, you might ask yourself, all right, these topological symmetries, they're all over the place. Well, not really. If you took a model with the full ON symmetry, so if you had a loop model based on Brouwer, there wouldn't be any such topological symmetry. Because in Brouwer, if you had a loop going around, well, that loop would be given a factor n. That's the rules in Brouwer, and there wouldn't be anything to do with it. So no topological symmetry in the system with full Brouwer or full ON symmetry. With open boundary conditions, you can try to do something else. So now you have Temple ellipse with no element closing the system. You can still have a loop going around everybody. You can do that. But in fact, it happens in that case that it is equivalent to the UQSL2 Casimir. And anyway, if you go from Brouwer to Temple ellipse with open boundary conditions, then you know what you have is UQSL2 system. So there is no topological symmetry if you allow crossing. There is no topological symmetry near a boundary. So at least it's not an. There is one of few examples I know that the categorical symmetry plays an explicit role in an interacting system, and not in the realm of topological phases. There's probably a use for this in the context of quantum loop models. I don't know. I was wondering about this. Not sure. And then I would like to conclude with an advert for Paul's talk on Friday. So the question of realizing topological defects in lattice models is very important, not only for practical reasons, but also for conceptual reasons. I think there are a lot of properties that are true, obviously, in the continuum, and that people assume will be true for any real regularization of the field theory. And I don't think that's true. I think there are big subtleties there, so I think it's a field that requires much more thinking. I haven't worried too much in my talk about explaining exactly how to define this topological defect on the lattice, but the point is it can be done. Finally, last but not least, thank you everybody, and have a nice lunch.